Absolutely, absolutely. But the thing is, it doesn't replicate what Doug's situation was. The same thing's happening with that bee pollen test I told you about, the neonics versus the bees. The big complaint as I'm slowly pouring through this data is that the way the bees were fed the neonic pesticides is not consistent with how they would have actually gotten it in nature. Like in other words, I feed my bees throughout the winter, or throughout the early spring and late fall, sugar water, to let them get their energy stores up. They put the neonics in the sugar water, which is not how they would get the neonics in nature. They would get them off the plants they were pollinating. And that doesn't seem like a big deal until you realize the concentration of crap in that water. It's a totally different concentration. You're getting imagine drinking 1,000 Red Bulls versus drinking one, and then releasing a study that says Red Bull is bad for you. Yes, your kidneys would liquefy if you drank 1,000 of them, but that's essentially what's going on with the study with the bees on a smaller scale, the same percentage scale. So anyway, that's why I have to replicate using the same stopwatches they were using, essentially. All right, so I am going to go ahead and crunch this data over in L3. You guys think about the errors. What would a type 1 look like, or be? Saying there's a difference when there's not. Saying that the thumb and the finger have different speeds when they don't. Type 2, therefore, would be? Saying they do what they... Saying they do. Saying they don't have the same speeds.
What really they do?
Excuse me. I lost my train of thought there completely. It's funny, I was turning my head sideways and I was like, what was I just saying? I was just saying something. Saying they have different speeds when they don't, that's a type 1. And saying they don't have different speeds, you know what the rate. I'm having a hard time talking up here. You know what the rate. Which is worse for you guys, in your opinion? Type 2 would be worse? Type 2 would be worse? Love it. Love it. Why? Just out of curiosity.
Because you'd be recording wrong time.
Gotcha, exactly. Because if you miss the difference, if a thumb or a finger was actually making a difference but you missed it, you'd be reporting on a wrong time, maybe too slow or too fast. Kids might be getting state records that didn't deserve it, or kids might not be getting state records or going to state when they should have. So yeah, type 2 could definitely be worse in that case. Of course, a type 1 could incite, all kinds of quality controls that don't need to be there. Oh, the thumb is faster, everybody must use the thumb. That's annoyance, but I think...
What was the time?
What was the time?
Yeah.
Oh, 22.96.
22.96.
And we're going to see, you guys are getting damn close to it. If you look at your numbers, you were getting damn close to that time. We could run T-intervals if you want to see. So there's my differences. I did real quick different calculations there. Zeros, 0.16s, 0.06s. You have to realize, in a swim competition, those are significant. You saw how close those times were. I mean, 1600ths of a second. The world record was beaten by 500ths of a second on that video. So 1600ths of a second is an eternity in swim time. So we got to get down to the precise, hundredths of a second, which is why we use the stopwatches, which is fantastic. Okay, let's test it. We're using a t-distribution again, yes? Oh, one thing I do want to check. I want to check one thing before, I want to check to make sure there are no goofy outliers. It's hard to see if there are because your guys' data is so close together, but I'm going to run a real quick couple curves to see. So I'm going to run a histogram on L3 with a frequency of 1. And I'm also going to run a box and whisker. Remember this from back in 243? It's okay if you don't. We'll come back to it again and again and again. So let's do a zoom stat. Whoops. I'm going to be a thin mismatch. Oh, I see why, because I forgot to press 1. Okay. Oh, look at that. God, look at that. That's interesting. There actually are outliers.
Oh, wow.
There actually are outliers. Let me break this up a little bit more for you. Yeah, your data is pretty bell-shaped, but we actually do have extreme values. Extreme values. Cassidy, I bet you yours is 1. Yours were off by 1.5 seconds, and I guarantee this is you out here. I think anyway. Just because I noticed that. You said 24 and 22, right? So if I trace out to there, I think that's probably you out here by 1.5, 2 seconds off, yeah. That was, no, not bad. We have to know what to do with that. Do we leave it in? Do we take it out? We leave it. Why do we leave it? It's part of the data. But what do outliers also sometimes want you to do? Go back and see how it was created. Maybe it was deviant from the way the other ones were created. So I always echo leaving things in. But with averages, do you see how outliers could pull you the other way? If you have too many outliers on one side of a distribution, the average is going to head towards those, and it might get artificially inflated on a few data points. However, we also have 2 outliers down here. So I'm not thinking we're going to have too much asymmetry with that. We've got a bell curve. This is much further away than those 2, but I'm tempted to agree. We can run it both ways if you want. We can run the test with and without the outliers and see what happens. That's something else we can do. Let's leave it in for now. But do you see my concern about outliers? Just keep that in the back of your mind when you're doing studies. You don't want to make the Jared mistake, right? Jared ate Subway, lose weight. Maybe. It's funny, I was at my PT on Tuesday, and there's a diet regimen. I want people to definitely get changed for PT. And it said, Jose lost 100 pounds on blah, blah, blah. And I'm like, wait for it. Results not typical. Like in a doctor's office. You know, it's like, come on, people. It's not typical. Anyway, let's run the test, shall we? Let's run that t-test in a doctor's office. Well, it's advertising. It's marketing, right? I'm not saying it's legit. We're just testing a two-tailed. Yes? Does not equals? Does not equal? Yeah, good. Let's take a look. Whoa, sorry. Let me turn everything else off. Hang on. Although you saw what we needed to see right now. Turn these plots off. There we go. Here she comes. There's a buttload of area. And that's a buttload of area. Remember why it shaded both sides? You're not giving it a choice, so it's doing both simultaneously to test. And a lot of area. 84% of the area. Test statistic is negative. That tells me that your thumbs were actually a smidge faster. Now, you wouldn't know that. I put your thumbs in L1 and your fingers in L2, and then I did L1 minus L2. So you didn't see me do that quick calculation. I did L1 minus L2. That came back negative on average. That means whatever numbers were in L1 were smaller than the numbers in L2, which means your thumbs were a smidge faster. But not by enough to be statistically significant. So yes, there's a difference, but you would almost think there has to be some difference, right? They're not going to be exactly the same. But this comes back and gives us some scientific support. There's your test statistic. Negative 0.2, excuse me. Negative 0.2, that's a huge difference. Negative 0.2, standard deviations. That's essentially at 0, yes? It's essentially at 0. P-value, huge, 84%. Lots of support for your null hypothesis. Hard to support the research hypothesis, isn't it? It's hard to believe the parents' claim with this data, isn't it? It's hard to say, oh yeah, thumbs and fingers are completely different. That says they're not completely different. That says they're essentially the exact same thing. So, conclusion, it does not appear that there's a difference in thumb and finger time. Could we be wrong?
Yeah.
Always. Type 2 false negative. But you guys weren't worried about that anyway, were you? You were about type 1 error, I think, if I remember correctly. I think you were about type 1 error. Oh, you were about type 2. Ooh. Maybe we lower confidence then. Yeah? Right? But of course, I don't care how much you lower confidence, you're going to have a hell of a time finding anything other than a huge p-value. Unless you lower confidence to like 5%. In which case, well, the parents won't know what you're talking about anyway. But you've just basically shown there is no merit to the claim that there's a difference. Go ahead.
Do you have data from other classes on that?
I don't. I never saved this data, but it always comes out with the same result. Just so you know, I've never once gotten data. You guys are the most consistent as far as the times. I've never seen times as consistent as yours. I usually get some that are off by like 2 or 3 seconds.
Wow.
So you guys are the most consistent. But even, you got to realize, you're super consistent on the second scale, but you're also, remember those graphs we had up, widely varied on the hundredths of and tenths of a second scale, which is kind of cool. There's that little box plot in the middle and those goofy outliers. Shelby, yeah?
How do you lower confidence on it?
You just decide to, in other words. So in other words, it wouldn't change the result of this at all. You just say in the beginning, I'm not going to test at 95% confidence.
But we don't put the confidence.
I know, see, Shelby's got a very good question right here. You don't put the confidence in. You also never read the confidence in research articles. They just give you a p-value. And the implication is when they say things p is less than 5%, that means they were testing at 95% because they're comparing it to 5%.
Oh,
You see, you can pull it from, very good point, you can pull it from context. So when they say p is less than 10%, you're like, oh, they must have been testing at 90%, not 95, which means they're trying to avoid a type 2 error. So that's a great question. You're right, it never says, that's why I keep saying, we'll just keep testing at 95%, checking p-values versus 5% and call it good. You can see right now, with a p-value of 84%, you'd have to lower your confidence ridiculously to get that to be outside. The interval would have to be like this wide, right? That's ludicrous to think about. I mean, it's ridiculous to think about that. But you're right, you never actually read it anywhere. Good, very good.
Well, but, so that's why you see you have to determine your confidence level before.
A priori.
So that you can't
Yes,
see
man. Because what you don't want to do is get a result. Because here's something that also happens sometimes. You might get watch this bastard move. So you're on this test, two-tailed. Let's pretend for a moment that these were far less shaded, but still over 5%. Let's say they shaded at 7%, not 84%. What the hell? 8.4%, not 84%. So 8.4% is still bigger than 5, right? But if you then say, oh, but I know the thumbs are faster, so let's change the sign on the hypothesis to be less than. That'll take that 8.4%, whoops, that'll take that 8.4% and remove half of it, which means it'll now be at 4.7%, which means it's snuck under 5%. Don't you ever do that! I catch you doing that crap, I swear to God. Find you. We'll have words, strongly worded words. Appendages will be discussed. So that's why it's got to be a priori is the phrase before you run the test, and you stick with the results. If you think there's something there, replicate the test again, get more data, but don't fudge your results. This is why Harrison Ford was running in The Fugitive, remember? I keep bringing that up. This is why Harrison Ford was running, because somebody fudged the results. Cool, which one you guys want to turn in? Commercials or stopwatches? Commercials it is? Okay, make a separate pile up here for that then. Perfect. And we'll catch you guys on Tuesday.
Indeed.
And we'll talk about V-brakes versus cantilevers. And how Max helps me do science sometimes.